Good morning, everyone. Welcome to today's edition of the YCLIP program. Before we start, we will kindly ask, I would like to remind you of the following housekeeping rules. Unmute yourself if you want to speak. Raise your hand, you'll be called to speak. And also, please turn off your video if you know your background is not nice. So before we commence, we will kindly ask Prof. Kluche, please, are you on board?
Hello. Yes, sir. Good morning. Good morning to everyone.
Yeah, good morning.
Good morning.
Good morning.
Good morning, Prof.
All right. So I can hear everybody as clearly as possible. So we will start in the next 6 minutes. It's exactly 10:10 a.m. So we are going to commence the session with your hello, good morning once again.
Good morning.
Good morning.
Good
Okay, so
morning.
Good morning.
and how are we doing?
Good morning. Yes, sir.
Doing well by the grace of God. How
Thank
about you,
you.
please?
We are
So,
fine. What about
God
you?
bless.
Okay, so a bit of reminder about the housekeeping rules. Please mute yourself if you are not contributing, and then turn off your video if you know very well your background is not clear. And also raise your hand if you want to speak. So before Professor Cloutier steps in, we would like to do a little bit of exercise. So I'll be sharing my screen soon. How many of you, can you all see my screen?
Yes, please.
Okay, so,
Yes, please.
okay.
Yes, please.
So we will be dropping a link in the chat. Please follow that link to join this. So we are going to ask you about what you learned from the course you took earlier, that course you took last week. So before we commence, I will drop the link in the comment section for you to, so you'll be able to participate in this survey. Can we all see the link?
Yes, please.
Yes. So please use that link to describe in the chat 3 key climate concepts you learned from the e-course, so the course you took earlier. So we'll be waiting for your responses. Thank you. Please, are we there? No one has responded so far. So describe in the chat. So when you use the link, the link will lead you to this platform. You see this very view where this question will be displayed on your phone, where you can enter, you'll be allowed to type in. So when you type in, you will see your response on the screen. And no one has responded so far. So we are waiting for your responses. Thank you. The responses are coming in. We have climate change, we have level rise, adaptation, and climate change mitigation. So only 3 people have responded. Five so far. And we are about 75 on the call. Nine, 10. And also be reminded that this counts into the selection, the 25 people we are going to select at the end of the day. So if you are there and then you are not contributing, you are doing that at your own peril. 18 so far. Climate models, temperature, adaptation. 60 more to go. Thirty so far. We have 4 minutes more to do this. So I'll be reading out a few of the responses if Luce comes in. So somebody said, I learned about gender representation in waste management and planning for unusual climatic events. And 2, carbon budget has been drawn by IPCC to determine the maximum amount of carbon emissions the world can emit, whilst maintaining average global temperature to meet the goals set by the Paris Agreement. Good. I learned about climate change and how it works. Oh. Mitigation and adaptation, a guiding principle in environmental policy and law, elements of climate change, climate funding and green bonds, climate indicators, mitigating cloud change and greenhouse gases. And then we have climate change indicators, precipitation, projected change and climate mitigation. The precautionary principles, principle of negotiation and adaptation. 52 responses so far. We are still waiting for you. We have about 27 more to go. And be reminded that this counts to your final grade. And this is going to determine the number of people we are going to select to do the project. This is all counting to your final project. The 3 concepts of climate and length include solar variability, volcanic activities, and changes in the carbon cycle. It was stated that aerosols play a significant role in warming the Earth's surface. Good. Mitigation, a process of lessening the impact, the risk associated with climate change. Sea level rise, agriculture and deforestation.
Unknown caller.
Okay. Since you all have access to the link, you can continue to send in your responses. But before Prof. Kluche steps in, I would like to acknowledge the following people for putting together this. So first and foremost, I would like to thank the Executive Director of CCSE Climate Change, Center for Climate Change and Sustainability Empowerment, Mr. Hussein Kasim, for putting together this. And then Mr. Solomon Kojo Hagan, who is the implementation chair, who has been in contact with you. And then a special thanks to the special program assistant at UNITA, Mr. Lucas Terra. And before Prof comes in, I don't know how many of you know who Professor Kluche is. You all know her as the current head of Department of Physics, but there is more to her than most of you know. Her research interests span from climate change, solar radiation modification, and sometimes even health. She was the lead author for the IPCC State Assessment Report, and she's the current vice chair of Working Group 1 of the IPCC. Professor Kluche, the floor is yours.
Thank you, Terry. And good morning to you all. I'll
Good
share
morning.
no, which one I'm sharing? This one.
Good morning.
So I'm following what you already learned from the online platform. It looks like this will be just a tutorial for you, especially those who have finished taking up to 3 courses on the online platform. So give me a minute. I want to show my face to introduce myself. Just 1 minute. Show my face. I want to open my camera. Okay, before. Open my camera. Oh, sure. Okay, you have seen me. Okay, so as Terry mentioned, I'm the head of physics department and also the vice chair of Working Group 1 of the Intergovernmental Panel on Climate Change. I'm sure you have heard of this institution through the course as you did it. So I'll put up the video so that we have maximum connectivity on the internet, if you don't mind. So this was just for the introduction of it. Thank you. Okay, so whilst on it, you see on the first panel, a global temperature anomaly reading. So the different lines of an animation, it's showing different institutions taking measurements. And you see the blue one is from the Met Office, Hadley Center, the UK. The green one is from NOAA, the National Climate Data Center. Then we have Berkeley Earth, and then the red one from NASA, GISS. So you can see that all the institutions, their measurement correlates, and it shows clearly that what the different institutions are showing is actually the truth and the evidence of global warming or climate change. I'll use the words or the terms interchangeably, and I will explain also the difference between them. The picture below in the lower panel shows how global warming has been over the years as measured at the top panel. So in the 1880 to somewhere 1930, we see a clear warming, a clear negative anomaly. So negative temperatures, which shows that any individual year average from any individual year record from the average record shows a negative temperature. Then in somewhere in the middle of the plot between 1940 to 1980, we have these different patterns of warm years and cold years. Then after 1980 till now, we only have warm temperatures. That convinces us that the globe is warming and warming continuously. And it's also an evidence of climate change. Other evidence of climate change, which is also shown on record with examples or evidence, is glaciers that are melting. So in the 1914 compared to most recent year, 2004, I didn't get a picture of the most recent year, but then the way you see the pictures of snow or ice cover in between or during the 1914 compared to 2004, we see that the ice are melting, and that is a clear change as well. Global sea level rise between 1870 to 1990. We were having an increase of the sea level with 1.7 millimeter per year. In recent years, we have moved to 3.16 millimeters per year of rise in global sea level. So it's another indication of climate change. Coral reefs help with the marine environment, and they are not able to grow efficiently because the carbon dioxide that is a lot or in abundance in the atmosphere also affects the concentration of carbon dioxide in the ocean. And so it's making the ocean acidic and affecting the growth of coral reefs in the ocean. So marine environment is also struggling. When you come locally, this is the temperature, maximum temperature of Accra and minimum temperature of same Accra, and a period between 1960 and 2018. You see that the line of average line shows an inclined format. So temperature is rising or shows an increasing trend for maximum temperature and also for minimum temperature. You see that even the minimum temperature rise is steeper when you compare to the maximum temperature. So which shows that night temperatures are rising even faster than the rate at which the day temperatures are rising. This is the local evidence of climate change. This is temperature over Accra, and I'm sure all of you know about Accra. So from the early 60s to couple of years back, like 6 years back, that is how the trend shows. If you have most current dates or most current data, it shows a continuous rise of temperature, both for minimum and maximum. Even for rainfall, when we do a different periods in time to check the changes in rainfall, we are able to clearly see how the peak of the season has shifted over the two periods. The same with maximum and minimum temperature. So you see that red is at the top and then there's a blue line down. It also shows that over the most current period, the mean monthly maximum temperature is higher over the period than the far back period, like earlier years. Same with the minimum temperature. And as you can see that again here, you see that there's a bigger gap for the minimum temperature than even the maximum temperature. So the night temperatures are increasing with a very fast rate, or the frequency of warming in the night is higher for Accra. So this is to just show you that locally we have the feel of the climate change as well. The other evidence, as we speak, as at 2023, the global temperatures have risen by 1.36 degrees Celsius, which means that if you look at the rates at which the temperatures are increasing, as at 2024, this figure had gone up, so 1.36 degrees Celsius, and it will probably rise further by 3 degrees or even more by 2100. So we normally use the end of the century as our reference year as well. Regional temperatures are rising, you can clearly see for Accra, and even in countries that have winter temperatures are also rising. Cold nights or cold days and nights and frosts are becoming rare. So we are not getting as much cold days and nights as we used to get, and frost as well. We rather have more hot days and hot nights, and heat waves have also increased. If you read the news, in last year, there are a lot of countries in the Europe and then in the US which had a lot of heat waves, and it affected a lot of people. Some lost their lives. Extreme rainfall and flooding events have become more frequent, and thus we also experience it in our part of the world. Then we have frequent heat waves all over, in many cases around the world. Extreme drought, which we feel, and wildfires as well. In this part of the world, we experience extreme drought and wildfires as well. These are all affecting everybody. And this is affecting even agriculture, and food is becoming scarce and more expensive. We're experiencing this as well. So the question is, why are we even concerned? The impact of climate change is affecting our environment and has the potential to destroy our very existence. So we want to understand what is going on and how we can curtail what is going on. This is affecting our habitat. It's affecting the air we breathe, the water we drink, and of course, the food that we eat. So we need to be concerned. Now, what is climate change? We've seen the evidence of climate change, but then what is climate change? In science, or scientifically, we say a significant shift in the mean state and event frequency of the atmosphere. So if you can clearly show that, if you can significantly show a change, then you can talk about the climate or the change in any variable of the atmosphere. Then you can talk about climate change. So if you use the diagram in the slide, I will use this to do a comparison. So where you have these stripes of blue compared to the stripes of red, you can clearly say this has a significant difference. So we can say this is a significant shift from the negative anomalies to a positive anomaly. This is very clear. It's also clear to compare any of those patterns to the middle part where we have a lot of variability. So this middle part where we have some warmth and some cold periods or years is also another change, because there's an epoch year which when you can compare with the clear red zone and the clear blue zone. So we can say 1, 2, 3 places shows a significant shift. So this is how we define climate change. It doesn't need to be just temperature. It's any variable in the atmosphere or any variable we use to describe the atmosphere is can be used to define climate change for a significant shift in it. So if it is rainfall that has changed significantly, we can talk about that as a definition of climate change. If it is wind pattern that has changed significantly, if it is humidity that has changed significantly, you can still use for the same definition of climate change. I want to make it a point here that climate change is a normal component of the Earth's natural variability. So if human beings were not on Earth, we still expect climate to change. The reason we are concerned is the rate at which these changes are occurring. So naturally, the Earth would have taken its time to change, I will call it naturally. But the rate at which it is changing is not natural, and it's causing a lot of abrupt changes in the atmosphere. And so that's why we are concerned. And today we'll also look at why, or the causes, why the climate is changing, the causes of the change. So let me also make another point here. The stripes that you see, the different levels of the ticks. So for each one, we call it variability. It is when you're considering a group of them compared to another, then we can talk about the change or climate change. Otherwise, each one that's showing a different level, we say variability. So if you look at the blue part, there are a lot of different levels of the blue, even with the part that has the we'll say a lot of variability, where we have some red on top, some blue on top in the middle here. It's also variability. So we say climate variability. Even in the zone that is all red, we still have variability in the annual recording. So in some years, record something lower than others, some record higher than the others. That is called climate variability. But then if you want to talk about change, then I explained earlier on, a significant shift in these periods over time, yeah? Okay, so the difference between climate change and global warming. I explained already climate change is that significant shift. Global warming may not be necessarily a significant shift, but because we see or can show that even with temperature, this warming shows a significant shift from some cold or some cold season. We say it's climate change. But then this part alone can be warming, and then we can call there's a global warming. Okay, so we use the words interchangeably, but then they have their differences also. So climate change includes the warming itself and side effects of the warming. So the warming in the atmosphere is causing, let's say, heavy precipitation or rainfall. It's increasing wind speed. It's causing droughts. And that's, we can clearly say it's climate change. So whilst global warming can be described as climate change itself, global warming itself is also causing other variables in the climate system to change. So we use the words interchangeably, but they are not the same. It depends still on the contexts that we are using it. Now, what is the cause of climate change? Climate change occurs when we have imbalance in the incoming radiation and outgoing radiation in the atmosphere. I will explain that comprehensively in the coming slides. So we have the sun's radiation coming in. We have the Earth's radiation going out. When we have imbalance, then we have the climate change occurring, but that should happen over a period of time. Then we can have climate change. So when we have an increase in heat trapping greenhouse gases in the atmosphere, it raises the Earth's mean surface temperature. And I will explain this. That's kind of a summary to it. So the levels of greenhouse gases are higher now than any time in the last 800 years. The reason we are concerned. Now I will explain. We'll do a little bit of physics. So now we are going to do the science of all that I have mentioned earlier on. The sun's energy is the major driving factor of the atmosphere. Its energy is released to the earth as a radiation. So it comes as heat, electromagnetic spectrum, or electromagnetic radiation, or electromagnetic energy. I'll be using them interchangeably as well. And right, of course, the sun's radiation travel as both particle and wave. Those who are reading physics will understand this statement. I will not go into it further. The radiation reaching the earth is affected by gravity. It's affected by magnetism, as the earth is a magnet. It's affected by the composition of the atmosphere. So the atmosphere contains gases. So depending on the concentration or the combination of gases in the atmosphere, it can affect the radiation of the sun reaching the earth, or the reflection of the sun away from the earth. The distance of the earth to the sun can also affect the radiation reaching the earth. We are talking about the sun as the major energy input of the atmosphere. Then the angle of inclination, how the sun's or the earth is positioned to receive the sun's radiation. So you realize that the middle or the area around the equatorial region receives more sunlight because it's actually closer and more like 90 degrees receiving the sun's radiation. And the areas that are at the poles, the north and the south poles, the sun's radiation reaches them at a certain angle less than 90 degrees. And so radiation also is affected by the angle of incidence of the sun. And then we have, of course, there are other energy input, which is the other heats, like the ones that we produce through our factory production from the industry, from burning of fossil fuel, driving of cars. Those other energy input are also there, but then they are insignificant compared to, or negligible compared to, the sun's radiation. Is the major energy input. So this is how, like, pictorially we measure or we discuss the Earth energy budget. So we have the solar radiation coming to the Earth or reaching the Earth, and this energy or radiation gets reflected and or absorbed by the component of the atmosphere. So let's say the white and the green, the blue spaces are the atmosphere, and then the green space here is the Earth. So, and the ocean, though the earth and the ocean are in the green spaces. So before the sun's radiation reaches the earth, part of it is reflected by the component of the atmosphere. Part of it is reflected by clouds, of course, which is also a component of the atmosphere. And you have part also getting absorbed by the atmosphere. So by the gases in the atmosphere. Then sun reaches the earth. That gets to the earth can also be reflected by the earth's surface, depending on the color or what we call albedo of the earth. You can just get some reflected back to space. Now the earth radiation also, and then the rest is also absorbed by the land and then the ocean. The earth itself also releases radiation, and that is the one that is shown in red arrow. So the radiation that's supposed to get out or is released by the earth, some also get out to space, some also get absorbed by the atmosphere, some get reflected by the atmosphere. So that's like the general concept of radiation from the sun and radiation from the earth into space. So most of them, they do a lot of interplay within the atmosphere, and we'll have to have questions to answer in the course of time. I'd mentioned albedo. So depending on the color or what we call reflectivity of the atmosphere and of land, the solar radiation that's supposed to come from the sun to the earth can get reflected or can get absorbed by the components of the atmosphere and also by the earth's surface. The whiter it is, the more reflective they are, or a surface is the more reflect, apart from water. So water, though white, when you look at water through a radar satellite, it shows black. So water is actually in the dark spaces or dark color zone. But then snow is white, sand is white, or once the white sand is white, and those reflect a lot more, same as clouds. When they are white clouds, they reflect a lot more of the sun's radiation than when we have dark clouds or dark surfaces. So these all play a role in the Earth energy budget. Now the question of how much, so I'm now taking you into physics, the concept of why we're getting global warming and the associated climate change. How much solar energy does the Earth absorb? We want to assume the Earth receives, we know the Earth receives the sun's radiation at one side at a time. Because when the